So that's last we have discussed about the extravascular administration of the drug. Following one compartment model, we have seen the model, then we have seen this graph. Okay, then all the phases, that is the first absorption phase, then the C max, then post absorption phase, then the elimination phase. So all the four phases we have explained, and finally after derivation we got an equation, that is C is equal to, that is equation 3, C is equal to K into F into D0B divided by Vd into Ka minus Ke into e raised to minus Ke into T minus e raised to minus Ka into T. So the next step will be the assessment of parameters. So important parameters to assess after extravascular administration following one compartment model are the Cmax, Tmax, elimination rate constant and absorption rate constant. These are the four parameters has to be find out. So first we'll see the Cmax and Tmax. The graph you have already explained. The point at which the maximum concentration reaches, that is called as the Cmax on the top, and the corresponding time is called as the Tmax. Okay. So we can say at peak plasma concentration at that particular point, the rate of absorption is equal to the rate of elimination. Okay, the rate of absorption is equal to the rate of elimination at Cmax at a particular point. So we can say there at that point the rate of change of concentration of the drug is equal to 0. This is the rate of change of concentration of drug is equal to 0, or we can write the dC by dt is equal to 0. dC by dt is equal to 0. For that equation, that is the concentration of drug after administration or extravascular administration, that equation we got that the third equation. That third equation is equal to 0 at Cmax. At Cmax, that concentration is equal to 0, or we can write that equation 3 is equal to 0, that is Ka into F into D0B divided by Vd into Ka minus Ke into e raised to minus Ke into T minus e raised to minus Ka into T is equal to 0. That is equation 4. Then we will be going for the simplification of the equation 4. Okay, we will be going for simplification. 2 exponent you can multiply by the common factors, that is K into F into D0B divided by Vd into Ka minus Ke. Then we will be doing the simplification. So we are not writing all the steps, directly writing as we are simplifying the equation 4 and we will get the equation 5. There is a simplified equation we will be writing directly, so that you have to by heart the equation, that is Ka into e raised to minus Ke into T is equal to Ka into e raised to minus Ka into T. Sorry, that equation 5, there is a small mistake. It is written as Ka into e raised to minus Ke into T. It's actually Ke. It is Ke. Equation 5. It is Ke into e raised to minus Ke into T is equal to Ka into e raised to minus Ka into T. That is equation 5. Okay. You got the equation 5. Then you will be converting that the equation 5 into its log form. Okay, you are converting the equation 5 into its log form. So you will get log Ke minus Ke into T divided by 2.303 is equal to log Ka minus Ka into T divided by 2.303. That is equation 6. That's the converted into its log form. So we got an equation. In that equation, that is in equation 6, the T, there is a T, you can see there is a T, that T represents T max, because we have derived and simplified the equation at particular point, that at C max. So the time corresponding to the C max is T max. So the T where that is there, it is given as it is a T max. So we can substitute the T with the T max. So we will be substituting the T in equation 6 with T max. Then again there will be a simplification. Again there will be simplification of the equation 6. So after simplification, again we will be writing the direct equation. The steps we are not writing again here. So you have substituted t with t max, and after simplification you will get t max is equal to 2.303 log Ka by Ke divided by Ka minus Ke. That's equation 7. So you got the equation for t max that you have to by heart it. Because the assessment of C max and t max, there are a lot of equation, a lot of steps for simplification that we are not uh, writing all the steps. So directly will be writing the equation. So you have to by heart the equation for t max, C max, etc. You have to by heart it. No other way. Okay. Then C max. So you got T max, that is 2.303 log Ka by Ke divided by Ka minus Ke. Then C max. So C max can be obtained by substituting equation 7 in equation 3. This equation 7, the last T max equation, you are going to substitute in your first equation, that's equation 3 you will be substituting. That means in the place of t, you are going to substitute this t max. So it will be a complicated equation. Then after simplification again you will get a C max. That's why we are not writing the steps. Okay. So that's why we will be writing only the final equation. So that is the method. Method you have to write. You will be substituting the t max value. That's equation 7 in equation 3. Then after simplification you will get C max. Then that C max equation you have to by heart. So C max is equal to f into d0 b into e raised to minus ke into t max. Okay, this C max is equal to f into d0 b into e raised to minus ke into t max divided by Vd. That is the equation for finding out C max. And there is another alternative equation to find out, or as another simplified equation to find out C max. That is C max is equal to 0.37 into f into d0 b divided by Vd. That is a two equation to find out C max. Okay, so these are the first two parameters, that is T max and C max. So all the conditions you have to explain. Typical plasma concentration, the rate of absorption is equal to the rate of elimination, so the equation 3 is equal to 0. Then we will be going for some simplification steps. That 2-3 equation you have to by heart it. So you will get T max and C max. These are the two parameters. Another next two parameter will be the important one, that is the elimination rate constant and the absorption rate constant. Then the elimination rate constant. For most of the drug, the rate of absorption is always greater than rate of elimination. Okay. If a drug is administered through the extravascular route or through the oral route, we can say, or through the oral route, then always the rate of absorption will be faster and the rate of elimination will be at a slower. If you compare absorption and elimination, always the rate of absorption will be faster. So we can say the absorption exponent. I told you that the rate of absorption is always faster, much faster than rate of elimination. So this absorption exponent always approaches 0 much faster rate than elimination exponent. There are two exponents we can see, that is e raised to minus ke into t, that is the elimination exponent, and there is a e raised to minus ka into t, that is the absorption exponent. So this absorption exponent becomes 0 much faster than the elimination exponent. So elimination takes place at a slower rate. So when the absorption complete, the changes in the plasma concentration depends only on the elimination rate constant. So when the absorption complete, told you the absorption takes place at a faster rate. So when the absorption completes, then there will be only the elimination phase, or the elimination phase, and it is characterized by the elimination phase. Or we can say when absorption complete, the changes in the plasma drug concentration depends only on the elimination rate constant. Once absorption complete, then the rate of change of drug concentration in the body depends only on the elimination rate constant, or it is characterized only by the elimination phase. So we can write the equation 3. We are excluding that absorption exponent, that is e raised to minus k into t. That term, full term, we get cancelled or it is reduced, because we are assuming that the absorption is completed. Then the equation reduces to C is equal to k into f into d0b divided by Vd into k minus k into e raised to minus ke into t. Now included only the elimination exponent, that excluded the absorption exponent. So we got the equation at the elimination phase. C is equal to K into F into D0B divided by Vd into K minus K into e raised to minus Ke into T. That is the equation 10. Then we'll be converting that equation to its log form. Okay, so you will get log C is equal to log Ka into F into D0B divided by Vd into Ka minus Ke minus Ke into T divided by 2.303. So converted that equation into its log form. So you got a linear equation. That is log C is equal to log K into F into D0B divided by Vd into Ka minus Ke minus K into T divided by 2.303. So you got a linear equation. So you can plot a logarithmic graph. That is by taking the log C versus time. We will be taking log C versus time. That's the log C on the y-axis and T on the x-axis. So you will get a straight line, and from the slope you can find out K. That is K is equal to slope into 2.303. From the slope you can find out K. That is slope into 2.303. Okay, and the y-intercept will be the remaining part in the equation. That is K into F into D0B divided by Vd into K minus Ke will be the y-intercept. Okay, you have plotted log C versus time and you got Ke from the slope. The remaining you can get it from the y-intercept. Okay, that is K into F into D0B divided by Vd into Ka minus Ke. Okay, that is that is we can also represent by the whole unit can represent by the capital I. We can make use of that representing instead of writing K into F into D0B divided by Vd into Ka minus Ke. That you can replace by writing the capital letter I. That capital letter I is equal to K into F into D0B divided by Vd into Ka minus Ke. That's a method. So that's a method to find out the elimination rate constant. So when you are going to find out elimination rate constant, you have to mention all the assumption or the fact, that is the absorption exponent approaches 0 much faster than elimination exponent. Because what is the reason? Reason is that the absorption takes place much faster rate than elimination. So when the absorption completes, only the elimination rate will be controlling the concentration of the drug in the body. So then it will be characterized only by the elimination phase. By that statement you can exclude the absorption exponent and you can write it as C is equal to K into F into D0B divided by Vd into Ka minus Ke into e raised to minus Ke into T. Then you can just convert that into its log form. Okay, so log C is equal to log K into F into D0B divided by Vd into Ka minus Ke minus Ke into T divided by 2.303. So we can plot the graph, linear equation, logarithmic graph. So we'll get a straight line, take the slope and find out Ke, and y-intercept will be the remaining part of the equation. Then there are other methods to find out Ke. That is, Ke also can be find out or can be estimated by using the urinary data. For this we will be making use of the plasma data, that's the blood plasma drug concentration data we are making use. But instead of that, we can make use of the urinary data to find out K. That is by the rate of excretion method and also by making use of sigma minus method. There are another two methods. By making use of urinary data, we can find out elimination rate constant. One is the rate of excretion method and another one is the sigma minus method. That we will study separately. Okay. Then the last parameter remain after extravascular administration is the absorption rate constant. That is an important one. Okay. So the K can be determined by different methods. It can be different. There are different methods to find out K, absorption rate constant. One is called as the method of residual curve fitting method, or it is also called as feathering or peeling method. Most popularly it is known as the curve fitting method or method of residual. It also known as feathering or peeling method. Second method is the Wagner-Nelson method. Third one is called as the Lou-Riegelmann method. So there are different methods to find out this absorption rate constant. In that we will study at least two methods we will be explaining here. One is the curve fitting or method of residual and the Wagner-Nelson method. So the method of residual we have to explain it more, so that I will explain it in the another video. So another voice clip or in the video I will explain the method of determination of absorption rate constant. So in today's class we have seen the measurement of assessment of parameter including Cmax, Tmax and elimination rate constant after extravascular administration.